Hello, hello, hello. We have the same paper as the previous presenters. I will quickly go through the paper again, but just in English. So in this study, the authors wanted to classify images from the microscope. They had 4 different types of cells, just images from time-stretch microscope. And usually you need to stain the cells with some antibodies or something else to validate to which type of cell does this particular cell belong to, but that's very inconvenient, and it's better just to look at the picture and decide which cell it is. In order to do that, they designed a neural network. They use deep learning to augment the imaging with high-speed and robust classification system to represent different cell types. They used three different models: convolutional neural network, k-nearest neighbor, SVM. They used a DAM optimizer, and you can see the metrics here. So CNN looks like the best option. It shows the best result for all types of cells. Their neural network looks like this. So we have an image as an input. Then we perform convolution. We apply max pooling, then convolution again, max pooling, convolution again. Then we flatten, have a full connection layer, and 64 nodes, and the final layer 4 nodes to perform the classification. In order to make the neural network more specific, to remove the noise, they also reprocessed the data. They performed flipping, removed some noisy images, and so on, just to make the model more clear. So there are 3 cell types in our dataset. They're a bit imbalanced. So, the minority is MCF7. We have 3 different groups: is training data, validation, and testing data. But among these data sets, they are balanced. So we tried to perform our own architecture. We did not repeat the architecture from the paper. So we used the original image, 180, 180. We rescale it into 0 to 1. Then we do max pooling, and we reduce the convolution, 64, 32, 16, and then we have only one final full connection layer, 128, with the activation function ReLU. We train it on 10 epochs, and we achieve high accuracy of 0.97. Pretty much the same as in paper, although the model is very different. Then we tried to play around with the architecture. We do 32, 32, 32. And it gives us pretty much the same result, 0.98 on 10th epoch. Actually, even 4 epoch is enough to reach more than 0.9 accuracy. The third architecture is 32, 64, 32. We still get the same result. Nothing much changes. So what we also try to do, actually the data set is pretty big, and it takes 1 day to train the whole data set, so we actually trimmed the data quite significantly. So we tried 272 batches, and the training, the efficiency is still high. So even if we reduce the number of images, the neural network works pretty well. And there is no much difference with 1084 batches. So it means that convolutional neural network perform very well, even with small number of images. What we also try to do, we compare different activation functions, and it looks like a DAM optimizer is the best, as an optimizer, and the final layer activation ReLU is much better than softmax. In fact, softmax reaches 60% accuracy very fast and then just steady stays there, while rectified linear unit it just steadily grows until 98. So out of 3 architectures that we tried, we choose the second one as the most efficient. Now we had an interesting idea to use the final layer of the CNN as a feature extraction tool from the images and feed it into the SVM decision tree and random forest. So it works like this. We have the same neural network, but the final layer we throw into the SVM. And in here we use linear kernel for SVM. So here is the SVM performance. In paper they report 77%. We were able to achieve 70. I think it's pretty good. Assuming that we trimmed a lot of data. We removed maybe 80% of images away from the data set, so we only trained on 20%, and it reaches 70%. Notice that for one cell type, THP1, the number of false negative results is very high, and especially THP1 is mixed with PBMC, so the model cannot distinguish between these 2 different cell types. The same problem is with decision tree. The accuracy is also around 0.7, and also THP1 and PBMC are often mixed. Other cell lines are distinguished pretty well. And the random forest also shows 68%, very close to the numbers given by the paper. So now we can compare, we calculate sensitivity and specificity for different models for different cell types. So it looks like MCF1 was the easiest one to distinguish, and you can see sensitivity for SVM and specificity for SVM is the highest. So SVM is the best model in this case. So overall, CNN showed the best performance, classifying all 3 types of cells. A change in the sample size and convolution architecture did not significantly affect any performance. SVM decision tree and random forest we were able to build from the last layer, and these models perform worse than CNN. Moreover, they can't distinguish certain cell types, and it was not a problem for CNN. So CNN is the model of choice. Here we just compare our model with the model in the paper. And that's how we did data pre-processing. And just before coming here on stage, we finished our 2 hours of training for random forest with a complete set of data. And that's, we had result of 92% accuracy, right? Yeah. That is the complete set of data. Previously we did only 20%. This is 100%. It took more than 2 hours. And we were happy to see this result just before coming out here. So conclusion, CNN model achieved the best performance compared to other classifier models.